So welcome back to the video. I'm going to increase the pacing a bit from here on out, since this tutorial series wasn't originally meant to go on for this long. So I'm going to start this video by adding the logic needed to give collision detection to our pieces. To do that, we first need a new variable called current piece. This will hold the index of the piece we are currently using in our game, and have used it in our get node over here and in our select color function over here. I have also moved the nodes that were over here to over here instead as the default value of our current x variable. After that, I have created a function called DoesPieceFit. Again, you can just copy everything by pausing the video. Now, something to be careful of when recreating these nodes is to not reuse variable names. It can cause all kinds of unexpected bugs. I actually ran into this myself. I accidentally reused a variable name without realizing it, and it caused a bug that took me a while to fix. I will explain how this function works later on, but basically all it does is that it checks whether the piece fits there or not. And after that, back in our event graph, I have the DoesPieceFit function over here. So we are checking whether the cell we want to move to is already occupied by another piece or our border. If there is nothing over there, we move the piece. And we basically do that same check on all of our keyboard event nodes over here. Again, based on the direction we want to move. So yeah, to test this out, I'm going to run this project. And you can see our piece is not moving past these borders. So our collision detection system is working fine. So before I explain how these nodes work, we need to first understand how we handle rendering in our game. So in simple terms, we first generate our screen, and this thing that you see over here is our screen, just like our canvas for drawing stuff on it. And then we have the playfield array, and our playfield array has our borders, which is marked by the index 9, and a tetromino piece that is over here, the L-shaped tetromino piece. And we can't move any pieces that are already in our playfield array, because it's now part of the playfield itself and not a piece that we can actually control anymore. And the zeros that you see over here are empty spaces. And then we have the tetromino piece that is drawn on top of the playfield, and this is the piece we can actually control in our game. So we are constantly redrawing the playfield and the tetromino every single frame. Handling the rendering this way allows us to prevent leaving a trail behind every time we move our pieces. Also, modern computers are now quite fast, so this shouldn't affect performance. Now to explain how our function over here works. So I'm going to use the same diagram over here, and suppose I wanted to move this piece down. Our function would basically simulate what would happen if our piece was down here, without actually moving our piece in our game. Then our function would check if there is something blocking our way or not, by comparing the part of our piece that has the x on them with the integer values stored in our playfield, which are these zeros over here. So in here, the integer values of the playfield that has the character x on them is 0, and 0 means it's empty space, and our function would return true as this is a valid move. There is nothing blocking our way. But if I were to move the piece here, then we can see one of the x's in our piece is in the same cell with the integer number 6 in our playfield. This means there is something blocking our way, and our function would return false. Similarly, if I were to move the piece over here, our function would return false because the integer value in these two cells over here is 9 and not 0. So basically, the x's in our piece should overlap with the cells in our playfield that has the integer number 0 for it to be a valid move. Next, we need to add the logic that moves our pieces down the playfield every second. I have already added the nodes that does that over here, which is also connected to the event tick node through the sequence node. This sequence node will execute the nodes connected to it one after the other in a sequence, thereby helping us to separate the movement logic from the rendering logic and keep everything nicely organized. So over here, We are checking if there is anything blocking the piece from moving down every 1 second. If nothing is in the way, we move the piece down. But if something is blocking it, then we do a couple of things. Firstly, we convert the piece into being part of the playfield itself. Going back to this diagram, you can see our piece over here can't move down any further because there is another piece blocking it. When this happens, we convert the x's in our piece into playfield indexes, with the index being current piece plus 1. We add 1 because our tetromino array starts at 0. So for this specific piece, it would be the index 2 plus 1, which means 3. So we would have a bunch of 3's over here in place of our x's over here. After that, we reset the current x and y values, reset our current rotation, and randomly select a new current piece. So if I were to run this to see if everything's working fine, you can see our piece is moving down the playfield and I'm not pressing the keyboard. So it's moving on its own, and when it reaches our lower border, it can't move down any further, so it stops moving, becomes a part of our piece, and we spawn a new piece to control. Also, when I display the current playfield's indexes on our BP plane, which makes up our screen, we can better see how our pieces become part of the playfield. So you can see how the numbers are changing when I set the pieces down. Now we need to add the logic needed to convert the rows that are filled with pieces to lines. So to do that, I have added the nodes from the completed pin of our for loop over here and moved the nodes that reset our pieces below it over here. So in here, we're going to loop through the height of the piece. It should be within the boundary of our playfield. We start by assuming there is a line. Then we check each row within our piece for any empty spaces. If we find any empty space, or if it is taken up by a line already, then we change our line boolean back to false. But if our assumption remains true, meaning we found a row filled with pieces, we're going to change the indexes in that entire row, which we're using to represent a line. So if I were to run our game again and try to get a row filled up, you can see the row that we filled our pieces with now has a line over there. Now we need to delete any lines after a short delay of about 1 second and then move the pieces above to the line downward to fill up the gap. To do that, I have created a new array, also called lines, which stores the row indexes of any line. Then in our rendering logic, from the completed pin of our for loops for rendering our pieces, I'm checking if there are any entries in the lines array over here, and if there are, we start a 1 second delay. Then for each line stored in our lines array, we move the elements above to our line, column by column, until we reach the end of the row. We're also going to change the element at the topmost row to 0 as we move through the column. And after we have gone through each of our lines in our lines array, we clear any entries in our lines. So to just run the game again, I'm going to try getting a line in our playfield. So you can see we got a line here, and after 1 second, we replace those rows. Now it's time to finally add our game over functionality. For this, I have created a new blueprint actor called BP Game Over. Inside it, I have a text render with the words Game Over. You can also customize the text and its color over here. And I have a plane under our text to give more contrast to the words over here. Back in our Tetris blueprint, I have tried to make everything look a bit more nicer since we have so much nodes now. So I have moved the input nodes over here under our Tetris game loop, and I have added some comments and organized everything a bit. So to add our game over functionality, I have the is game over boolean over here to check whether the game has ended. If the game did end, then we spawn the game over blueprint on top of our playfield. And the way we determine that is by checking if there is already a piece in the spawn area. So if I were to run our game and try to get a piece inside our spawn area, so you can see our game over logic works. And with that, we reach the end of this tutorial series. We now have a functioning Tetris game. It doesn't look great, but you can easily add more graphics, effects, and animations to make this look a lot more nicer. I have also uploaded the full project to my Patreon, so if you'd like to support me and get the project files, visit my Patreon, linked in the description and comments. So yeah, thanks a lot for watching, and see you later. Bye.